Good morning and welcome to the 23rd annual exhibit of hydrogen and fuel cell technologies and batteries. We've been here for 23 years discussing the innovations, the new developments. It's a changing field. I'd like to invite you all to sit down and have a coffee or tea on the house. The ladies will be serving drinks and be prepared for some very interesting developments in the field of electrolysis. I'll be talking to Professor Dr. Andreas Friedrich, who's head of the Department of Electrochemical Energy at Deutsches Zentrum für Luft und Raumfahrt, DLR. Please welcome with me Professor Dr. Andreas Friedrich.
Yes, hello, Brian.
So, good morning.
Morning.
Before we get into the new developments that you are presenting today, perhaps a short introduction on the DLR?
Yes, so DLR is the German Aerospace Center. It's one of the large national research centers in Germany. Of course, aeronautics, space research are important topics, but also energy. And we belong to the energy sector, and my department develops electrochemical energy technologies, meaning batteries, fuel cells, and electrolyzers.
And electrolyzers. And there we have the topic for today, of course. Electrolyzers are made of many things, but the important things are related to efficiency, stability, and how much current they produce.
Right.
How much hydrogen they produce per current.
Yeah.
So let's get into the details. What exactly have you uniquely developed recently?
So what I wanted to present today, and we have also an exhibit at our booth, is a specific component used in the PEM electrolysis, but which would be also in a similar way used in other, like alkaline technology. And you need this so-called gas diffusion layer or porous transport layer in order to get a homogeneous hydrogen production over the surface area, and in order also to, of course, to contact the electrodes. And here in this you see on the lower side, three different transport layers or gas diffusion layers which are used in the technology, which is, for example, a mesh, a sinter titanium, which is, however, very expensive. Also, felts can be used. And we have now a new innovation on this gas diffusion layer. And you see that here on the right upper hand side, we produce now gas diffusion layers completely by plasma spraying, making them a graded porous structure. And when you look at the left-hand figure, where voltage is plotted versus current density, meaning the lower the curve, the better, because you need less electricity for the hydrogen you produce. Then you see that this microporous layer that we produce gives you an advantage compared to traditional transport layers. And this is shown, I continue here with this slide, where you see now a comparison. Again, you see the porous graded layer, and then a comparison with other gas diffusion layers. For example, the mesh, which is quite inexpensive, but has a higher, you need more energy, more electricity in order to generate the same amount of hydrogen. So this comparison is done for the same amount of hydrogen produced for the same current density. And the sinter titanium is a very expensive component, and our new developments have as good performance as a sinter titanium, but are less expensive, much less expensive.
Mm-hmm. Of course, when we hear a drop in costs, that's always fascinating. People also talk about the lifespan. It's the total cost of the unit over time that is really interesting. Yes. So is it too early to make announcements about the lifespan of this gas diffusion layer?
Well, so far we have very promising results, but as a research institution, we have only limited test possibilities. So we test for thousands of hours, and we see no degradation in this with these components. However, of course, we have not the field experience that we have tested them for 40,000 hours. So far we can say for thousands of hours these components are completely stable, and we don't see more degradation compared to the traditional components.
That is, despite the reduction in costs, it's comparable to titanium also in terms of lifespan.
Yeah, we assume that, yeah.
So this is a significant reduction in cost for the overall electrolysis unit.
Yes, we think so, yeah.
Well, this is a fascinating approach. We always talk about comparative technologies, and what I find so interesting is that the manufacturers, they like to profile their PEM electrolysis or their alkaline electrolysis. You do work on several different systems here. Yeah. What are the advantages of PEM electrolysis if you compare that to other technologies you work with?
Well, we have a lot of experience with alkaline electrolysis, which is a very mature and very robust technology. And PEM, the polymer electrolysis, of course, has more dynamics. So we can demonstrate that it's more dynamically operated, and especially at partial loads. So when you go to partial operation, the hydrogen purity is much better compared to the alkaline electrolysis. So, but in general, I think that we will see that there will be markets, applications for all three major electrolysis technologies, because they have strengths and weaknesses. So under stationary conditions, probably the alkaline technology is very robust and stable. So the PEM will have his strengths in the dynamic operation when you have when you need fast changes of operation, and also the high temperature electrolysis had its strength when you look at, for example, synthetic fuels, because high temperature technology can produce not only hydrogen from steam, but can also reduce CO2 to carbon monoxide, giving you the synthesis gas that you need for synthetic fuels, for example.
You mentioned the flexibility of the PEM technology. Does this have any bearing on, for example, the introduction of renewable energy? We all know that the problem of renewable energy is the sun doesn't always shine or shine at the same strength. Sometimes it's a windy day, there's lots of energy, sometimes there's no wind. So does this give the advantage to PEM electrolysis when we're trying to recover optimally the production of renewable energy?
Yes, I think PEM electrolysis has several advantages. One is the coupling with renewable energies, especially photovoltaics, for example, where you have where the irradiation can very fastly change when you have when the sun leaves suddenly, for example. And also the power density is very high of PEM electrolysis, meaning that also your the area you need is less compared to alkaline technology. So due to the higher power density, you may be able to introduce it in areas, for example, fueling stations where you don't have much space.
So those are all interesting distinctions. I've been here for 15 years. I think you've been here at least as long. We see each other once a year here. There's been a significant shift in the landscape of this exhibit. By that I mean the quantity of people exhibiting electrolysis technology, which is the production of hydrogen through a supply of electrical current, has increased. The number of square meters occupied by this form of technology has increased. What is this new focus on electrolysis all about? What does this tell us about where we are in the fuel cell and hydrogen industry?
Well, I think that we have seen a strong interest in electrolysis in the 80s of the last century, because there we had this oil crisis. So this was the first major interest in this technology. Then again, the fossil prices were quite cheap, so inexpensive. So then again, more interest was on the fuel cell technology in order to achieve new applications which are which enable a better application, higher efficiency, and so on. But now, with more renewables in the power sector, the importance of green hydrogen increases again. And hydrogen is also needed in transport for fuel cell cars, but also in the chemical industry. And electrolysis is the technology available for green hydrogen. And that's why you see this interest.
I should add that we will have time for a question or two from the audience. If you do have a question relating to electrolysis, this is the man to ask. One of the problems, I suppose, in renewable energy is the fact that we need to store it. We also need to transport it. So this is a running debate. We've seen this also in the past few years. If you have a wonderful source of wind energy, the wind turbines in the north, but you have the consumers in the south of Germany.
Yes.
I don't know where you're from, Bavaria or where. But
Stuttgart, I'm from.
okay, so we're talking about long distances with potential losses on the way, and then there's the question of you can transport electrical energy conventionally, but that would mean you'd have to use it when it arrives.
Yeah.
So we have this big shuffle around renewable energies, and we also know that if we're going to meet the climate goals, the reduction in CO2 emissions, we have to decarbonize a lot of stuff. We have to be able to store renewable energies.
Yeah.
So here's the question. Electrolysis is a wonderful way of producing hydrogen, but the big debate, it seems to me, is there any alternative to storing potentially gigawatts of electrical energy produced in the north other than hydrogen? When you look at all the technologies you're involved in, what are the alternatives to large-scale electrolysis if you want to store gigawatts of energy?
Not many. Hydrogen is, of course, one possibility. Then you can store this in terms of liquid fuels, which, of course, are much easy to transport. But hydrogen is the basis for this path as well. So that means that you have also to have, you lose also some efficiency during this conversion process. And then, of course, the third alternative could be to use this as heat, so power to heat. So these are the only technologies I think they're available, because with the batteries, it's unrealistic to expect such a gigawatt hour storage capability or terawatt hour that we need.
I always find this question interesting because we're not simply talking about whether an electrical car is better than a hydrogen fuel cell car. That would depend upon the consumer needs partially. And there's nothing wrong with using both of them in the same vehicle. So we're not talking about consumer products. We're talking about a fundamental grid problem and a national supply of energy. And it's a question of scale.
Yeah.
So that's very interesting. Right now, this is almost an unfair final question, I suppose, but right now, about 1% I've heard of the hydrogen produced today is actually produced via electrolysis.
That's correct, yeah.
Now, nevertheless, when we see here the potential to reduce the price of the gas diffusion layer, that is significantly reduce the price of an electrolysis unit without loss of efficiency, with comparable production to the expensive titanium alternative, this is dollars and cents. Is there going to be a shift to electrolysis as opposed to other conventional ways of producing it, whether we need hydrogen as a storage facility, or is the industry, the electrolysis industry, really driven by renewable energy and by climate change decisions, policies?
So yes, we have to be realistic. So electrolysis was the major technology for hydrogen production in the past. And it lost the battle, if I may say, to natural gas, because when natural gas was established, steam reforming of natural gas was much cheaper for hydrogen production. So we have the the problem that natural gas is less expensive compared to electricity, and this will remain like that even if we have more renewables. So we need the political regulations which emphasize the environmentally friendliness of this path. And this will be needed in addition to the cost reduction that you can achieve by technology. Nowadays, regulations are completely against green hydrogen because all the levies, all the renewable energy levies are put on top of the electricity price, increasing the electricity price to a level that it's not feasible to compete with natural gas.
There's almost a tertiary question about the competition and the way it's voiced. Germany does have a fundamental problem with energy dependence. And renewable energy is one way of producing without using fossil fuel resources, which are relatively scarce in Germany by comparison with many countries, to produce its own source. So I don't know whether anyone's come to your department and say, we need electrolysis not because of simply the green energy factor, which is also interesting, not because it works as technology, it allows us to transport energy from one place to another with potentially fewer costs, but simply because Germany needs to produce a larger portion of its energy demands here in order to have what many countries refer to as simply energy stability, energy security. Have you ever been asked that question?
Yes, I think that is also a main driver for many, especially in industries, that they think that in future energy security will be very important, and if you reduce the bill for importing all this fossil energy from outside, of course this can be also an argument for the national economy in total. That you have more energy generated in your country.
And it's jobs.
Jobs.
This has been a fascinating talk. I've been talking to Professor Dr. Andreas Friedrich von Deutsche Luft and Raumfahrt. The booth is over here. It's D62. Very knowledgeable person. I think the conversation should continue there. This is the man to ask for technology questions which exceed my knowledge, but also for the broader picture of what's happening in the fuel cell industry, particularly with reference to this new gas diffusion layer, which is certainly going to be a plus to future electrolysis technologies. It's been a pleasure.
Thank you, Brian.
Thank you. Bye. And thank you. You're welcome to stay seated. There's coffee and other beverages served here, and we'll be continuing in very few minutes. We'll be talking to Professor Bin Rai and Hemant Didvania, who are going to be discussing on-site hydrogen production. They're from Green Hydrotech. So drinks are on the house.